Hey, what's going on, guys? GameOS here. In this video we're going to learn how to convert assembly code to x86 machine codes, and this is known as hand assembling. So we'll write a very simple program in x86 assembly language using the Intel syntax, using NASM, which is Net Wide Assembler, for just to make sure that I did this hand assembling correctly. And then eventually we will run the program in the online emulator, which would be running the operating system I've developed exactly for this kind of purpose of testing the hand assembled machine code. Okay, but first thing first, and without further ado, let's actually start writing some code. So first, I just want to write this code in assembly language. So I want to say move to I want to move the constant of 0x0e, and this is the bias code to output character to screen. Okay, then I want to say move to al, the actual character I want to output, and I want to print a. Very simple. So here I specify the character to print. Okay, then in order to actually make things happen, we want to call interrupt. So this is known as the bias interrupt. Call bias interrupt to print character. Okay, and this is known as int hexadecimal 10. And eventually, because we're going to be running this in the specific operating system which I've created, and this would be done from the shell. So if we don't jump back to the shell, then we're going to stuck forever. I don't want to avoid that, and that's the reason why we want to go back to shell. And here is an example of the for jump instructions. So jump, and then I specify the segment and then the offset. Okay, so this is the entire code that this is the entire assembly code that we will convert into machine codes. Okay, now just to give you an idea, where did I get this sort of values for those if you're not aware of assembly language that great yet. So here is a nice site covering the bias interrupts, which come up with very handy things to do, like reading sectors from a hard drive or floppy disk, printing to screen, scrolling, writing strings, whatever. So really lots of useful things could be found here. Okay, so now let's go back to our code. So I found a very nice document on the internet which is called hand assembly instruction handout.pdf. There would be the link in the description below this video where you can download this document. And like, it wasn't really trivial to find that decent information on this topic, and even though this one doesn't seem to be the complete guide, but it gives a very intuitive understanding of how to make this hand assembling, and that's the reason why I'm using it. And it has the most used it has the formats for the most used instructions, and this should be literally enough for encoding most of the instructions. And if one day I encounter some instructions that can be encoded using this guide, then I will probably be referencing some different sources, or just using the pre-coded codes from generated by NASM, but that's going to be a completely different story. So without further ado, let's actually go and try to assemble our code. So the very first thing to do, we have the move command here. It's a move instruction, and we need to classify what exactly we're doing here. So here we have the immediate value that we want to initialize AH with. So we have immediate to register instruction format and immediate to register alternate encoding. We're going to be using alternate encoding because it's just shorter, and the shorter the instruction is, the more instruction we can fit into the single 512 bytes, which is the limitation for my operating system. But anyway, just always better to keep things short, especially if it does exactly the same thing. So here is the format, and I will now type this in, and then I'll talk through this, trying to explain what this means in particular. So here let's define all the steps like one by one. So immediate to register alternate encoding. So again, immediate means immediate value. This is the immediate value, and to register AH is known as the register. Okay, so it's not a memory location; it's the register, right? Okay. So immediate to register. So 0 1 0 1 0 1 1, then W, then register, and then the immediate data. So immediate data. Okay, so what this means, so if we scroll up within this guide and have a look what W means, then we see that it specifies the data type. The data is specifies if data is byte or full-sized, where full-size is either 16 or 32 bits. So if we have a look at the table of registers, then we'd see that if we deal with either 16-bit register, so if we want to initialize 16-bit register with an immediate value, or if we want to initialize 32-bit register with an immediate value, in this case we need to replace W with 1. Otherwise, if we're dealing with 8-bit registers, we need to replace W with 0. Bear in mind the fact that we're going to be working in the real mode, 16-bit real mode, which is specific to x86 processors. We don't really need to care about the 32 bits. We don't really need to care about 32 bits registers at all. But anyway, we're dealing with the 8-bit registers. So as far as AH can be found here. Okay, this is AH, and hence we have W equals to 0. So what we can do next? So we can rewrite this, but instead of a W, we just place 0, and instead of register, we need to find AH in this table. So AH is equal to 100, which is 4 in hexadecimal. So 100, and then the immediate data. So we could have said just 0E here, but as far as we're writing in binary, so let's actually convert this quickly to binary. So this would be 0 0 0 0, and this would be 1 1 1 0. And now you might be wondering how the conversion from binary to 0 is done, and even though this is not the scope of this tutorial, let me quickly demonstrate how this can actually be done. Obviously, alternatively, you can use the calculator. You can use the calculator and just go to the programming mode and try to convert things using the calculator. But I want to quickly show you how things can be done. So let's consider that we have so let's say 1 1 1 1 in binary. Okay, so we know that this bit is worth 1, this bit is worth 2, this is worth 8, this is worth 4, and this is worth 8. Okay, so in order to convert this value to so from binary to hexadecimal, we need to, every time we have 1 and not 0, we need to add all the corresponding values. So in this case, we need to get the value for this, we need to add 1 plus 2 plus 4 plus 8. So let's try to do this, right? So 8 plus 4 is going to be 12, plus 4 is going to be 14, plus 1 is going to be 15. So 15 is in decimal, right? So let's say this like decimal, and in hexadecimal, we have F, because in hexadecimal we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. So these digits represent themselves, while letters, so A stands for 10, A stands for 10, B stands for 11, C stands for 12, D stands for 13, E stands for 14, and F stands for 15. Okay, so why I said that this value this value is E because it's 14. So we had the value like this. So it would be like only 8 plus 2 plus 8 plus 4 plus 2. So we have 8 plus 4, 12 plus 2, 14. Okay, so hence we have the 14, hence we have E. So this is how we can convert binary to hexadecimal back and forth. And we really need to be aware of this, because later on this binary format of the instruction will need to turn this into hexadecimal in order to be able to enter that in the hex editor. Okay, so in order to write in machine codes, we need to write in hexadecimal. That's kind of like how things are usually done. So I hope it's clear. If you're not clear like this conversion, you can just go to and just using the calculator, or you can search for some additional resources covering this in a bit more details. But for now, we just go for converting things by hands, and probably I can use calculator just to make sure that I did everything properly. So we need, so this is worth 8, and 1, 2, so 3. So 1 plus 2, 3, 3 plus 8, 11. So A is 10, B is 11. So we have B here. Okay, one more little step just to make life a little bit easier. So we can rewrite this expression the following way. So just to make it, so we know that in hexadecimal every letter or every digit represents exactly 4 bytes always. That's how it works. So we can just group them by 4 bits like this, and now this bit is equal to 4, it's worth 4, and the rest are zeros, hence in hexadecimal this is going to be 4. Here we don't have any like bytes equal to 1, so the value would be 0, and this is equal like 8 plus 4 is 12 plus 2, 14. 14 is E. Okay, so and eventually the x86 machine code instruction representing this single line would be B40E. Okay, now you might be wondering, so how can we check this out? So in order to check this out, we can just go and open the terminal in the current working directory if you have NASM installed. If you don't, you can try to reference the online emulator, the online assembler, for instance, or whatever. You can use whatever assembler, because it's the matter of the syntax. Even the syntax doesn't matter. It's the because from the machine code perspective, no matter what, if we use the Intel syntax or AT&T syntax, or like different assemblers might have a little bit different syntax for reference and say memory, like pointers or memory values. Anyway, in machine codes, this always should be the same. So how can we do this in NASM? I can simply say NASM minus av bin and print a dot asm and minus o and print a dot bin. And if it assembles, I want to use the xxd, which is the Linux hex editor, and I want to open the file print bin. So print a dot bin, and yeah, sorry guys, I need to comment out the rest of instructions because it just goes and it just assembles all the files. So I'm sorry for that. We obviously need to assemble only. Hold on a sec. Yeah, I just need to save this. Clear. Yeah, so now we have assembled the only instruction, this one, and you see like it gives us B40E, which is exactly the same value that we came up with just using our hands. Okay, so now let's go to the second instruction. I'll try to explain less and do more because the first one didn't assume any prior knowledge basically. So let's move further on. So here we do exactly the same format as before, because we want to put immediate data, which is ASCII character A, to the register AL. So the format that we're supposed to be using is the same. So we can just reuse this format here without any issues. So we just can reuse it here. But the difference is going to be in the registers, in the register and in the immediate data. So I still write this, W is equal to 0 because we're dealing with an 8-bit register. So here I put 0. And now we need to find the code for register AL in the lookup table. So the register AL is here. So 0, 0, 0 and 3 zeros. Okay, and then the immediate data. Now, in order to get this, we need to convert this ASCII character into the corresponding hexadecimal value. So you can use ASCII table for a lookup, but probably the fastest way is just to open the developer tools in the browser, wherever on whatever page, it doesn't matter. Then just type the ASCII character and ask this character code at, and it will give you the decimal value of this A. So now all you need to do is just to convert this decimal value into, where's my calculator? Convert this decimal value into hexadecimal value, and just go to hexadecimal, and we have 61. Now let's also convert this to binary. This would be 001 0001. Okay, convert it to binary. Yeah. I'm sorry. What have I done? Nope. Okay, just never mind. So 61. So this is 6, and this is 1. So we have 4 plus 2 equals to 6, and here we have 1. That's pretty much it. Okay, so now let's convert this binary instruction back to hexadecimal. So here we still have B, like in the above example, but here, one more important step, guys, I'm sorry. So just copy this and let's make the layout look properly. Okay, so here we have B, here we have 0, here we have 6, and here we have 1. So which means that the next instruction should be B061. So now to make sure that this is really so, let's just try to check this using NASM. Okay, so 2 instructions and we have B061. So we did everything properly, instruction matches, this is cool. Okay, so now the next thing to consider, we need to call the BIOS interrupt to actually print this character, and for this purpose we're going to be using int instruction. So now let's look, let's search for the int instruction in our instruction list. So where is the int? Yeah, int. So we have int and n and interrupt type n. So yeah, this is the one that we're supposed to be using, where n, where this type is simply the value. So we can just use, so this is used just, so this type works just like the immediate value. I'm wondering, do we have the type? No, we don't seem to have that. Well, because this is the special case. I believe this is treated as the special case. So let's just grab the format for a command. So here we have where is that? 1100 1101, and then the type. So I just need to, so I already have this in hexadecimal, so this should be 10 in hexadecimal, but yeah, let's turn this into binary. So this is 8 and this is 10, right? So let me just quickly check this out. So we are in binary territory, 1010, and in hexadecimal should be 10. Oh, should be 8. Oh, hold on a sec. Hold on a sec. Nope, no, this is wrong. Hold on a sec. In hexadecimal we have 10, and in binary Okay, sorry guys. What have I done? So no, it just be 0, 0, 0, 1, 0, 0, 0, 0. This is it. Yeah, it actually converts properly, or no, not exactly. So if we say 0, 0, 0, 1, 0, 0, 0, 0, and convert it to hex, it should be 10 in hexadecimal, which is 16 in decimal. Okay, so yeah, and now well, here we don't have we don't need to fix the layout because it's already just fine. Okay, so we only need to convert this back to hexadecimal. So 8 plus 4, yeah, 8 plus 4 is 12, and 12 is C, I believe, right? So 12, yeah, this is C. Okay, C. Now here 12 plus 1 is 13, so it should be D. So 12 plus 1, yeah, this is D. Okay, so D, C, D, and here 1, and here 0. So eventually this would result in CD10. Okay, so now let's check if we did everything properly, and let's try to use NASM to assemble the third instruction for us. And we have CD10, which is exactly what we want. So this is amazing. And we get one last instruction, and this might be a little bit tricky, but we'll nail it as well. So the trickiness is how to encode the addresses. So x86 architecture uses the little endian byte order, and we need to take that into account when we're dealing with physical memory addresses. So we literally need to reverse the address. So, but another thing to consider is something to know about the addressing in real mode. So this so 800s is the segment, and this 0x000 is an offset. And in order to turn this into the real physical address, so physical address, we need to make we need the following formulas. So we need to say this 800 hexadecimal multiplied by 10 hexadecimal, which is 16 in decimal, okay, and plus the offset 0x000, which would result in 8 thousandths and offset like this. But I told you that we need to use that x86 byte order is a little endian, so we need to reverse the order. So this would be like 00000008. Okay, so this is actually the value for our address of where exactly we want to jump. Okay, so bearing this in mind, we can now go and try to assemble this this instruction. So we have jump, unconditional jump to the other segment. Okay, so we have the direct intersegment. So we have this exact value. So this, I believe this is just like the immediate data here, or the type of the interrupt here. So just the constant value. We just deal with the constant value. So what would be the format in this case? To the same segment, we have to the other segment, direct. So here it is. So 1 1 1 0 1 0 1 0, and then unsigned, full offset, and selector. And this is what we're going to be using for our unsigned, full offset, and selector. Okay. And now let's assemble this. Now let's convert this to hexadecimal. So 8 plus 4, 12 plus 2, 14. This should be E. Yeah, this should be E, just like we did here. Then 8 plus 2 is 10. So this is A, and this is 0, and this is 8. Okay, guys, sorry. Yeah, I just forgot. Yeah, so here we actually. Okay, hold on a sec. I mean, the problem is that what I've written here is actually already, yeah, it's the hexadecimal representation. Okay, so this is already a hexadecimal representation. So here, to be honest, I'm not exactly sure like how the mechanism of this works internally. I just use my assembler to match the values and just to nail it, to master it from the practical perspective. So I can't provide any theory about this because it just I'm not sure what exactly this jump other segment, so unsigned full offset and selector means. So I guess that the selector is where we actually want to go, but I'm not sure what the unsigned full offset means. So I just can say that I just provide the proper values in binary and in hex. Okay, and this is how it's gonna look like. Okay, yeah, it takes a bit of a space. But okay, let me just type this and then I'll resume the video. Yeah, all I can say is that in binary instruction would look like this exactly. And now if we just bring this to a more human readable format, then we will have EA 00, then 4 zeros and 08. So which can be, well, this is my assumption. I'm not 100% sure that this is actually true, but I assume that so we have 1 2 3 4 5, okay, 1 2 3 4 5 6 7 8, yeah, digits. So 1 2 3 4, 1 2 3 4, and then EA. So it's just an alternate way to represent this. So what I believe that this is the physical address that we're dealing with, okay, just in the reversed order like we have here. I might be wrong though, so here guys, I'm sorry, because of the lack of documentation that I could find, I can't say this, that this is true for sure. But what I can say for sure is that this is the exact instruction that would be generated for this jump to the other segment. So that's what I know for sure. So let's check this out and have a look. And we have this EA004008, which is the case for us. Okay, so this is pretty much it regarding the assembling. And now one of the most exciting parts of the video, let's try to run the machine codes that we eventually came up with into within the emulator. So let's bring all the machine codes in. Okay, so then this one, okay, then this one, okay. So we can actually provide the, yeah, we can still, by the way, yeah, we can still give the commentaries to this machine codes as well. I think that is going to be a good idea. And this one as well, copy, paste. So here we have x86 machine code, okay. Okay, let's make it like this. So what we do here, here's the BIOS code to output character to screen, so we can initialize. Well, we could have used this as well. Probably let's do it like this. Okay, then we have character to print, and we can use this one. Then we have this call, and finally we want to jump back to shell. And this is pretty much it. Okay, so now let's enter this code and see the output, okay? So in order to start the emulator, here are the steps that you need. So we don't need this one anymore, we don't need this one. So if you navigate to the GameOS repository and just download the source code, okay, and then you go to copy.shell v86, and here is the button to select the image to load from. So just click this choose file and then go to downloads or wherever you've stored this. I have them on the desktop, so here's my GameOS source, and we need to make sure that we're using this GameOS developer pack that I've released today basically, and this GameOS.img, so this image, okay, and then just click start emulation. Okay, just waiting a little bit until it loads. Okay, you can choose a custom color theme just to make life a bit better, just to bring some kind of like fun to this project. And then let's go to the editor, and here we need to enter the bytes that we just came up with. So we just move this back here. Okay, so here are the bytes that we need to input, and let's make it always on top as well. And okay, so B40E. Sorry guys, first we need to specify the address. I'm sorry, just forgot that. So edit again. Now let's just clear this stuff. So go into editor. Yeah, first thing we need to specify the address. So we're gonna be writing on this specific address. This is specific to GameOS operating system. So just say 0500. This is essential, right? And now we can enter the bytes. So I say B40E, and then B061, and then CD10, and then EA004008, and hit enter. So now the bytes are in there, and if I did everything properly, if we run this code, this should be printing the letter A and drop back to shell. So let's clear the screen and try the run command. And here we go. So we just got our A being printed, but you see a bit of an issue here is that we don't really have a new line after, so we can alter our assembly code to add the new line. Okay, so let's quickly do that because the code is going to be very similar to what we've been doing so far, and this would just give a better, I believe, better interactive understanding of what's happening. So we just well, the simplest way to do this, we can just grab this entire part and paste it in, and so this would be the same, this would be the same code, so B40E would be the same, this would be the same, but here we want to well, actually we need 2 characters to be exact. We need 10, which stands for, yeah, by the way, 10 is in this is in decimal. In hexadecimal this should be A, right? Yeah, this should be 8 in hexadecimal, so no longer on top. So let's go to decimal. 10 hexadecimal A, yeah. So here this would be move I just don't want to say like this because I believe in assembly it just doesn't work that way, right? So A for a new line, okay. So here print char new line. Here we print the character A, okay. So the register is the same, and all we need to change, so B0 would be the same, and we just need to change to A, so it would be like hexadecimal 0A. So this is how this can be encoded, okay? And this is gonna be 0 and okay, let's quickly convert this to binary. 10 10, yeah. So yeah, 8 plus 2, yeah. So this is gonna be 0 and this is gonna be A, okay. And then we'll need to do the same thing to let's quickly check with assembly. Then we'll need to do the same for the carriage return, okay. Function F9. So yeah, and now we start from scratch again. So B40E, B0, and now 0A is the code to move A or to move 10 to AL, and then we execute. Okay, and a few more instructions. So like one last instruction to add here would be, okay, so this is all okay. So copy and paste. So here we want to print the carriage return. Carriage return. I hope I've spelled carriage properly. If not, I'm sorry. And here in decimal it would be 13. That's the code for carriage return. And this would be E. Nope, this would be D, I believe. So go to decimal. So 13 D, and in binary, yeah, this is it. D B00D. Okay. Yeah. So this should be it. So this is the code for the carriage return, just to print the carriage return. Okay. And let's add them here as well. So here we want 0A. So here char to print is A, here the new line, and it's not 061, it's gonna be I just didn't check this. B00A. Okay. So this is gonna be B00A. And here yeah, B00D, and I already made it here. Okay, so B00D. Well, I hope I did everything properly. If not, we'll just figure out this using NASM. Okay. Let me just make it full screen. So here we want to print the carriage return. Okay. All right, so now let's try to assemble and see if the codes match. So we have B40E, okay, CD10, B40E, B00A, which is okay, CD10, B40E, B00D, which is okay, CD10, and all this stuff. Yeah, so this is pretty much it. So now we can safely input this code, and instead of just having this, so let's go back to the edit. I'm sorry. Save. So let's clear the screen. Let's go back to the editor. Well, we can just replace the bytes, but on the other hand, we can just calculate the offset, so we can still keep the code for the very first one. So this would be 1. It's easier to calculate them here. So 1 byte 1, 2, 3, 4. You remember 2 digits represent a single byte. So 1, 2, 3, 4, 5, 6. So if I say 0, 5, hold on a sec. 0, 5, 0, 6, and let's try FF. Let's just shouldn't be doing this. Yeah, this is it. So it just replaces. So let's go again. So 0, 5, 0, 6, and 1, 2, 3, 4, 1, 2, 3, 4. Just replace with the zeros. I've erased what we don't currently need. Okay, so B40E, B061, CD10, and then 0506. We can go on. So again, B40E, B00A for a new line, and CD10 to print, then B40E, B00D to print the new line, and then CD10 to call the interrupt, and then the jump EA 00 1 2 3 4 0 8. I can use spaces, I cannot, it doesn't matter. So you can use spaces, you may not use spaces, it's all about you. Okay, and now guys, I hold my breath, escape from the editor, clear the screen. If I did everything properly, it instead of just printing the letter A, it also should print the new line. So let's see, and this is exactly what's happening here. So we've just we did call the run, and we can now see this A. By the way, if you want to save your work, there are 5 user-defined programs here. So prog 1, 2, 3, 4, 5. All these programs have placeholder message. So if you want to save, you can say save, and whatever program you have in the editor would get saved as either program 1, 2, 3, or 5. So let's store it as the prog 1. Okay, and let's new actually cleans the memory range in the editor, and then let's say load and 1, and going back to the edit. So we have our program here, and now if you want to extract this locally, you can just get hard disk drive image. Okay, and if you now go to, so if you want to play around with this locally for some purpose, you can just go to downloads and this undefined image. So this we can rename this to GameOS image, and if we open this using the built-in Linux text editor xxd gameos.image, and let's search for prog2. That's probably the easiest way to search. Yeah, so this is the sector for prog2, and this is the code. So from here and up to here, we have 512 bytes for prog1. So you can extract this from here using the dd command, for instance, or whatever else, or use a Python script to extract this for you. It's all on you guys. And yeah, and you can just then keep working with this program locally if you need this. So that's how it works. This is how we can translate machine code. This is how we can do hand assembling of this assembly code. So how can we convert this assembly code to machine codes? So this is pretty much all about it, guys. This is pretty much all about it. So I will now try to figure out how to encode more advanced instructions, because really lots of gaps and I have really lots of questions in this regard still. But if I come up with something decent, then I would definitely share it with you guys, so you would be able to do exactly the same thing that I do. Okay, so this is it from my side. Thanks for watching. Until the next time, and take care.